All right, scientific notation. You dealt with this in physics and in chemistry and things like that, but today we're going to talk about the background behind it, make sure we're comfortable on it. Some of you might not have ever seen it before, but it's a way to write a really big number or a really little number in a consistent, normal, standardized way. So here's the definition. Here's what you have to end up with. You have to end up with a number, and I'm just calling it A, times 10 to some power. Now, n, the power must be an integer. Integer, remember, something up here on the number line. Okay? Negatives or positives. And the number, this is not quite right. It has to be greater than or equal to 1, but less than 10. So can it be 1? Yes. Can it be 10? No. So it could be like 9.99, or it could be 1. That makes sense in terms of the bracket? So it can't be 10. If it's 10, then there's something we do and we switch it back to a 1. So that's kind of our definition there. So cross this out, the between part, and kind of circle that. So here's two numbers. This first one, we had a little computer issue here. That 3 is supposed to be an exponent. So this means 4.5 times 1,000. And this means 2.76 times 1 over 10,000. And I'm going to show you kind of how to make those work in a little bit. So, two little examples of scientific notation. All right, so let's kind of analyze example 1. 34 times 10 to the third. What do you think? Raise your hand if you think it's scientific notation. Raise your hand if you don't. Okay, we got about 4 votes for no, about 3 votes for yes. Someone who says no, since obviously if you're saying a no, then you must have an argument. Let's let you guys start, and the yeses can come back if they so desire. Who said no? All right, Katie, why do you say no?
Because if 34 is greater than 10.
Okay, 34 is greater than 10. So is it scientific notation? No. Very simple. All right, B. If you think it's scientific notation, raise your hand. Okay, I got about 5 yeses. If you think it's not, raise your hand. Got about 1 person said yes and no. Okay, that's interesting. John, you said no, so you argue your no point.
Well, I think it's yes.
Oh, you think it's yes? Okay. Who thinks it's no? Let's let the no's argue first. Drew.
0.5 is less than 1.
0.5 is less than 1, and our number has to be what? 1 or greater. So once again, is the scientific notation? No. Sad face.
Does that mean you can't multiply it, or does it just mean it's not scientific?
As presently written, it's not in scientific notation. We could manipulate it to make it in scientific notation, but as presently written, it's not in the correct form. And the goal is to understand and identify correct form. So let's give an example of something that would be. How about 3.4 times 10 to the 6th? Is that
Yes.
between 1 and 10?
Yes.
Power of integer. Sure. 6.8 times 10 to the negative 6. Is that? You bet. Does anyone recognize this one? 6.02 times 10 to the negative 23. That's a physics measurement. I believe that's the measurement of a mole. And a mole is a unit of measure in physics, in chemistry. So, all right, moving down. Converting numbers to scientific notation. If numbers are larger than 1, they will have a positive exponent. If they are smaller than 1, they will have a negative exponent. All right? Yesterday we learned that 10 to the third is 1,000, right? So here we have 567 million. Now, let's write this as a decimal. First of all, 5.67. And to do that, that would be times 10, times 100, times 1,000, times 10,000, 100,000, a million. How many more do we go? 6, 7, 8 spots. We have to multiply it times 10 to the 8th. And the reason we multiply it, Noah, times 10 to the 8th is because to move that decimal 8 spots, That's 3, that's 6, 7, 8 spots would then work. 10 to the 8th, a huge number. Huge number. All right. 100 million. All right, next one, B. Extremely small number. We still make it 5.6. But now we look, how many times do we have to move it? Let's count. And actually draw this with your pencil. 1, 2, 3, 4, 5, 6, 7, 8. One more to get in between 5 and 6, 9. So that's times 10 to the negative 9. When you move the decimal left, the exponent goes up. Notice which way do we move this exponent, or this decimal? We moved it left, so the decimal went up. In opposite way, when we move the decimal right, the exponent goes down. Someone else explained to me one time, they said, if the number gets smaller, the exponent gets bigger. Here, this number is getting bigger, so the exponent's getting smaller. So it's kind of a reverse relationship. Well, 567 million is becoming 5.67. Is that not getting smaller? So therefore the exponent gets bigger. It's kind of an inverse relationship. So here, 3.5. How many decimal places, Jalon? Count with me. Do I go more? No. So that's times 10 to the negative 3. All right, you try the last one. Work with your partner, see what you get. 53 billion. 53 billion. See what you get. Count by threes if that helps. Take that 53 billion and let's write this as scientific notation. Is that billion? Thousands? Millions? No! Sorry. It's trillion, isn't it? Is it thousands, millions, billions? That's billions, okay. So 5.3 times 10 to the how many? Till the 10th. Okay. All right. We good there?